to the first session of the 2020 National Hydraulic Engineering Conference. I'm Victoria Beal with the Ohio LTAP Center. I am so pleased to be able to partner with my colleagues who you will be hearing from over the next 6 sessions. I want to go over a couple of quick housekeeping items, and then I'm going to turn things over to Brad McManus. First off, I'd like to thank everybody who's already responded to the poll question that we have running. If you cannot respond on your screen for some reason, please just hit the escape button to take yourself out of full screen mode, and then the software should accept your answer. The next thing I would like to ask is that everybody who's an attendee, please look for the question box in the GoToWebinar panel. And if you would please drop me a hi or hello in there so I know that you've found the question box. That is going to be the way that we're going to accept questions throughout the entire conference. And we appreciate everyone sending in their questions throughout the presentations, because we have reserved time for questions to be read by the moderators to the presenters. And then also in the handouts area of your GoToWebinar panel, you are going to find handouts which are relevant to this session. They're going to be updated before each session starts to match the presentation that is scheduled during that session. If for some reason though you can't get those handouts to download, no worries. We have a section set up on our website, and I'll be sharing the location of the handouts and location of where we're going to put recordings of these sessions also, that you can access after the sessions complete. I appreciate everyone who said hi or hello in that box. We really want to make certain that you know where that's at so you can ask lots of questions of our presenters. I did notice that someone used the raised hand function. We're not using that during this conference because we do have over 500 registrants, and we just can't go through the audio unmuting of everyone to ask questions. That's why we're utilizing the question box. The other thing I would like to mention before I turn things over to Brad is that we will be using the same link for all 6 sessions over the next 3 days, including the virtual tour that Brad's going to talk to you about during one of the lunch times. So I believe that's all I had. Are you ready, Brad?
Yes, I am. Thank you very much. Well, I want to welcome everybody. Good morning. Some earlier than others. While everybody's logging in, I want to go ahead and go over some things. Just talk a little bit about the history here. Because of health concerns with COVID, we had to postpone the conference. But as you know, technology and information associated with hydraulics and hydrology doesn't stop progressing. And because of this, we felt it very important to transmit this information to a broad audience. And that's how this virtual mini conference came about. I'd like to thank Ohio DOT, LTAP, and their staff for the tremendous effort that they've done putting this together and making this a reality. Ohio stepped in and really offered to help even after hosting the 2018 National Hydraulics Engineering Conference, as many of you remember. Specifically, I'd like to thank Victoria Beal, who's just on, and Paula Hyman and Jeff Sire for their help in this. I also like to thank the support of the NHEC Steering Committee, which without all the help that I've gotten from Cynthia and all the others, that we really couldn't put this thing together. While framing the mini conference, we thought it very important to make sure that this mini conference was free. So that was one of the aspects that we had. And in the atmosphere of canceled classes and conferences, the need for training and information sharing became abundantly clear. We had a lot of we were slammed with applicants when we first put this thing out there to advertise. As many of you know, we normally run about 200 for the regular conference, and we reached our maximum of 500 within just a few days. But fortunately for us, Ohio's LTAP coordinator and the resources are helping us put this on, so that's been fantastic. We wanted to get the most important and pertinent information out there, and based on the abstracts we narrowed the topics down to resilience and aquatic organisms passage, 2D floodway modeling, 2D modeling sediment transport, scour and mesh generation. Then we have a session on scour, and then finally we have a national hydraulics perspective. And you should have been provided a brochure, which will have, has a lot of information. The brochure give you what is being presented, the abstract for the presentation, and a short bio of the presenters. So this is a fabulous document for reference, and I hope you guys use it and get a lot out of the conference. And with that, I think I'll be turning this over to Mike Hogan, who's going to do the resilience session. And so I don't know if Mike, if you're ready
Brad,
for that.
before you do that, did
Yes.
you want to finish up your poll questions?
Oh, yes. Thank you for reminding me.
No problem. I'll go ahead and close out the current one. And I can share the results.
Awesome.
So we've got
a lot of state
say,
transportation agency, which is I think
yes,
part of our focus.
49% there, and then we've got 37% private, and our federal and other partners, federal agencies and other agencies are 7% and 6% respectively, and 2% in academia. So I'm going to hide those results. Did you want me to run any of the other poll questions?
Yeah, do we have the one about the region? What region you're in?
I sure do. Just put that one up, and we had a extensive list of states that had been assigned to each region, but it wouldn't fit in the GoToWebinar software, so you're just going to have to self-select. So if, you know, someone in Florida feels like they want to move themselves into the Midwest, I guess they could do that through this poll. But
awesome.
You guys are great. We were up to almost 80% voted, so once we push over that 80%, I'll go ahead and close things out. That's saying something because we have almost 400 people on here. All right, I'm going to close it up and then I'll share those results. Okay, it should be sharing. There you go. So we got 32% in the South, 24% Northeast, and then West and Midwest are split 20-20, and 4% who've joined us outside of the 48 contiguous states. All right, I'm going to hide that. And I'll run the last poll question for the intro. And I'm going to launch it. And this is going to be everybody's favorite. What area are you most interested in? And again, everybody's voting quickly. We appreciate that.
Yeah, while we're waiting, it looks like we've got 378 attendees so far, so that's fantastic.
We have a question that came into the question box. Someone wanting to know if we hadn't hit the 500 maximum within about 30 minutes, could they share their link? The only problem with that is whoever you share it with is not going to get a certificate of credit to, you know, that they attended this session. We are planning on hosting replays of these sessions in a few weeks, and I'll have that information together and out to everyone who is registered for this conference before it ends on Thursday. So we'd prefer you not share your link, but I'm, you know, not going to be there to stop you if you do. All right, we're up over 80%, so I'm going to close that out and then share the results.
Wow, lots of bridge and culvert hydraulics.
Yep, 24% scour and then 11% for all the other categories. Okay, I'm going to hide that poll question. And then if you want to introduce your first presenter, Brad, I'll get the presenter status moved over.
Okay, actually, I was going to have Mike start the introduction with his session here.
Thanks.
Thank you.
Good morning. I'm Mike Hogan from Connecticut DOT. I'm the moderator for the session. Welcome again to the conference, session 1, Resilience. We have 3 great presentations today to start off the conference. Our first presentation is Designing Flood Resilient Infrastructure in an Era of Environmental Change by Jory Hecht. Dr. Jory S. Hecht is a hydrologist with the U.S. Geological Survey, where he is devising and evaluating methods to reflect ongoing environmental changes in design flood estimates. Dr. Hecht earned his PhD in environmental and water resources engineering from Tufts University in 2017, where he studied with Professor Richard Vogel. Prior to his doctoral studies, he worked at the Illinois State Water Survey and earned a Master of Science degree in civil engineering from the University of Illinois at Urbana-Champaign. Jory, please begin.
All right, thank you very much. Hold on one second. Just get to the right mode. Yeah, so it's great to be here with all of you, even though it's just in a virtual environment. So anyways, today I'm going to share some preliminary work on designing flood resilient infrastructure in an era of environmental change. And today's talk is on the last of a three-phase project run in cooperation with Federal Highways Administration that focuses on changes in peak flows. So as I mentioned, this is a three-phase project. The first phase, trend detection phase, looks at questions of where are changes happening and how are floods changing. This phase is complete and has resulted in the publication of several scientific papers. You can see these references in the handout that I've provided. And then the second phase drew from a large team of regional experts throughout the country. They're all pictured below. And this work focused on the questions of attributions, not just looking at how floods are changing, but why they're changing, what's causing these changes. And this, a report on this work with many chapters is currently in review. And then the third phase, which is the focus of my presentation today, draws from the first two phases and examines methods from the literature for adjusting key design events, such as the 100-year flood. So for instance, the 100-year flood today at a given location might not be the same as it was 30 years ago. These methods that account for changes are sometimes referred to as non-stationary flood frequency estimates, which means that the envelope of variability of floods at a given site is changing over time. While many people have contributed to this work, I'd like to acknowledge some key personnel for the third adjustment phase of this project. They are all pictured in the top row. So the four women to my left are my co-authors. Karen Ryberg, based at Dakota Water Science Center, is also the project manager. And then to her right are Nancy Barth and Angela Gregory, also from the Dakota Water Science Center, and Stacy Archfield from our headquarters in Western Virginia. And then last but not least, yeah.
I'm sorry to interrupt. Can you check your audience view panel? I'm getting some messages that folks aren't seeing your screen, what you're sharing.
Oh, okay, I'm sorry. So I apologize. The message show my screen came up on my other monitor, so I didn't see it as I was talking.
That's fine, thank you.
So basically, this is a three-phase project with detection, attribution, and adjustment phases. And then we're looking at where changes are, the detection phase looks at where changes are happening. The attribution phase looks at what is causing the change, and it drew from a large team of regional experts that you see pictured below. And then the adjustment phase, which is the focus of today's talk, looks at how to adjust flood frequencies for change. And as I mentioned a minute ago, the women to my left on the top row are my co-authors, and Julie King on my right is our branch chief of the Analysis and Prediction branch at the USGS, and she's been a great advocate and liaison for this project. So I'd just like to start with a brief overview of my presentation today. First, I'm going to review some more common approaches for adjusting design peak flows, such as the 100-year flood, for changing environmental conditions. Next, I'm going to use a case study in suburban Detroit to illustrate the importance of accounting for changes in peak flow variability. After that, I'm going to show how accounting for environmental changes can get a bit messy when it comes to selecting a design flood estimate that takes environmental changes into account. Now, while urbanization can indeed induce many different changes to peak flows through a multitude of mechanisms, here we're going to focus on the better known tendency for increases in impervious cover to increase peak flows. And then finally, I will conclude with a brief discussion of how these methods can be extended with some extra steps and cautions to make climate-based adjustments for those who are interested in incorporating any climatic changes into their estimates. So let's get into some existing practices for addressing changes in design floods. So one approach that's sometimes used is simply a safety factor. For instance, this might be requiring a certain freeboard height for a structure above the 100-year flood elevation. Another common practice is to adjust previously computed design floods using updated hydrometeorological data. This may include using the most recent USGS flow data or using updated extreme precipitation estimates from NOAA's Atlas 14 in a design storm simulation, or it might even include removing data from an unrepresentative period. So if you say have a dam that was built in 1960, it might not be worth including the data prior to 1960. Another approach is to simulate the effects of different historical or design storms on a watershed under current land use conditions. In addition, there are numerous, actually quite a few, statistical procedures for adjusting design events using trend modeling. More recently, the National Cooperative Highway Research Program commissioned a report that looked at a whole bunch of different methods from the literature and recommended using just trends in the mean annual flood. Now, one important thing to bear in mind about such an approach is that it assumes that small annual peak flows are increasing at the same rate as large ones. However, this doesn't match up with numerous prior studies that have shown that increases in impervious cover due to urbanization tend to magnify smaller floods much more than larger ones. One reason for this is that larger floods in undisturbed basins often take place when soils are already saturated, which makes the infiltration reduction effects of impervious cover much less relevant. However, adjusting design floods to current conditions remains a wide open research area. For this exact reason, the authors of the federal government's Bulletin 17C elected not to provide specific guidance on this topic. And indeed, there are many other approaches for adjusting design floods to reflect current environmental conditions. And I'd just like to give you a heads up for the handout that I've distributed, where we'd love to hear from you about your experience making these adjustments and any other methods that you've tried yourselves or you'd like to try or you think we should consider in our research. So now I'm going to get into my case study of the River Rouge in Birmingham, Michigan, to the northwest of Detroit. So you can see the graph in the upper right that shows that impervious cover in this basin has increased from just 8% in 1950 to 26% under current conditions, more than a threefold increase. And then the graph on the lower right shows the change in the log transform peak flows over time. These are natural logs, by the way, not log-based 10, as are often used in this type of work. And you can see that smaller floods, which are the blue dots, have increased substantially, while the largest floods at the site have not changed much at all over time. And we did a little bit of research as to why this might be the case. There are no major flood control reservoirs in the basin. And while rainfall has increased since the beginning of the record in 1951, we conducted a few analyses and compiled a few prior studies, which together demonstrated the importance of, or corroborated the importance of urbanization in driving the increasing trend in flooding that you see in the lower figure. So one thing that we sought to do is directly use this impervious cover information in a trend model instead of using time as a surrogate for it. So how can we go about doing this? Well, what we can do is we can apply the same natural log transformation that you saw on the previous slide, but instead of using time as our independent variable, we use the impervious cover, which we've denoted here as IC, as an independent variable. And we get a similar result. One slight difference that you might see is that the points representing the latter part of the record are closer together because, as we saw on the previous slide, the urban growth rate has slowed down considerably in recent decades. However, one of the key features, the reduction in peak flow variability over time, remains when we look at the basin's response to changes in impervious cover. You can see that the distance between the red trend line and the blue observations becomes smaller as the watershed becomes more urbanized. So to model the trend and So to model the trend in variance, we can square the model residuals and see whether or not they are also related to the impervious cover. They are. So we can also model the change in variance as a function of impervious cover. Then we add the estimates of the mean and variance conditional upon a given value of impervious cover, say the impervious cover in our most recent year of record, into the quantile function. And we take this, so we take the mean of the log transform flows conditional upon the impervious cover and the variance of the transform flows conditional upon current impervious cover, and we plug them in to a quantile function that allows us to estimate the design flood with an exceedance probability P. So if we're looking at a 3-year flood, the exceedance probability will be 0.01. And this is how we can incorporate changes in impervious cover into design flood estimates. So, however, we're not going to assume that models that look at trends in the mean and variance are always better, because with any time you add more complexity to a model, you also increase the uncertainty. So I'm going to show you how we went about comparing 4 of the different trend models that we're examining in this study for our site in suburban Detroit. So first, we're considering a no trend baseline case. Then we're considering a case when there's only a trend in the mean of the log transform flows. Then third, we're considering a case where there's a trend in both the mean and the variance. And then finally, in addition to looking at changes in the mean and variance, we're just going to go right to the percentile that we care about, which is the 100-year flood, or the 99th percentile of annual peak flows. And you can do this with a method called quantile regression, which doesn't even depend on selecting a probability distribution. And one thing that's nice about it is that it can recognize that different floods with different recurrence intervals change at different rates. You have the two, so here you see a little conceptual diagram. The 2-year flood increases pretty rapidly, the 10-year flood a little less rapidly, and the 100-year flood barely increases at all. So we wanted to compare this method to more traditional approaches that involve probability distributions. So before I proceed further, I'd like to highlight and reiterate some key questions for non-stationary flood frequency model selection. So first, we often ask which theoretical probability distribution should we use. While Bulletin 17C still recommends the LP3 distribution, we're exploring whether other distributions might be worth considering at some sites instead, or instead of going the distribution route, as I just mentioned, we might want to employ an empirical approach like quantile regression. The second question asks, is trend modeling worthwhile, or will it just introduce more error into our design flood estimates? And the third question is, are modeled flood change trajectories the same in calibration, or in other words, within sample periods, and validation, or out of sample periods? And in the interest of time and brevity, we're going to focus on the first 2 questions when we look at our case study. So let's get right to it. So question 1 evaluates the distribution fit. And as an example, we're going to compare just the 2-parameter log normal, otherwise known as the LN2 distribution, and the log Pearson type 3 distribution, otherwise known as the LP3 distribution. So we performed a non-stationary version of the probability plot correlation coefficient test that accounts for changes in the mean and variance of a flood record. I'm not going to get all into the statistical nuts and bolts of this right now, but in short, we're adjusting the observations for changes in trends when we do the distribution fits. And the objective, what you want to see on this graph, for a distribution to fit well, is that you want the black points to fall right smack on the red line. This indicates a perfect match between values from a theoretical probability distribution and ones from an observed annual peak flow series. We're especially interested in how well the upper tail fits because we're looking at the 100-year floods. Here we can see that the upper tail observations lie closer to the red line for the LN2 distribution than they do for the LN3 distribution, but that in general, both distributions fit pretty well, as the test fails to reject both distributional hypotheses. So we can proceed onward examining estimates with both the LN2 and LP3 distribution, bearing in mind that the LN2 distribution performed a little bit better in this particular test. So now moving on to our second question, will trend modeling make our estimates too uncertain? Or when is it worth dealing with the extra complexity of trend modeling? So to answer our second question, we first need to compute the trends in the mean and variance. Our models of the trends in the mean and variance show that for each 1% increase in impervious cover, there is a 4.5% increase in the 100-year flood due to the trend in the mean, and a 5.3% decrease in the 100-year flood due to the trend in the variance. And then we can run a Monte Carlo simulation or run Monte Carlo simulation experiments to see whether it's better to use a model with higher bias and lower uncertainty. So that would be a case where you just assume no change and you might have more bias, but you're going to have less uncertainty because you have fewer parameters. Or a model with lower bias and higher uncertainty. And would do this for data arising from an assumed probability distribution. And then to determine whether it's better to use higher bias, whether to use an estimator that has higher bias and lower uncertainty, or lower bias and higher uncertainty, we use the fractional root mean squared error metric, which accounts for both bias and uncertainty. And we run these experiments for many different combinations of trends. So we look at, trends in the mean and trends in the variance, and look at a whole bunch of different combinations, which you see there with the black dots. And we see for each combination, which one is the best, which of these four models performs the best, or in other words, has the lowest fractional root mean squared error. So let's start with a simple example. So if we have no trend in the mean and no trend in the variance, not surprisingly, the simulations tell us that it's better to use the model with no trends, because otherwise we're just going to add uncertainty without really improving the bias much or reducing the bias much. Next, if we have a trend in the mean but not the variance, you see that there's a big purple area that runs parallel to the x-axis because there aren't very strong trends in variance here. But if we have stronger trends in variance, we'll see that the experiments will tell us that it's better to use a model that looks at trends in both the mean and variance. So let's see where our particular site falls. So as you can see, here's a location where in this trend space where we have a 4.5% increase in the 100-year flood due to the trend in the mean, and a 5.3% decrease in the 100-year flood due to the trend in variance. So this experiment, which assumes an LN2 distribution, tells us that if we want to make that assumption, it's best to use a model that accounts for a trend in the mean and a trend in the variance. We can also do the same analysis for the LP3 distribution, and here we get a different recommendation. At our site, the simulations tell us that we should look at trends in the quantile or the percentile. So that means that we should apply quantile regression to produce a design estimate of this at this site. So this provides us with important information about how well these different methods might perform under different distributional assumptions, but it's not the only line of evidence that we're going to use to make the final judgment. So now let's look at the actual 100-year flood estimates. So these 100-year flood estimates are conditioned on the watershed's current impervious cover, approximately 26%. Again, modeling just a trend in the mean assumes that the variability of the annual peak flows is the same over the entire period of record. Clearly, this is not the case. Moreover, the 100-year flood estimate, accounting for just the trend in the mean, as you see in the purple bar on the bar plot, is way above the flood of record. And this is a 69-year record for your reference. As you can see in the graph on the left, there isn't any strong visual evidence that the largest floods are increasing. For this reason, we discard the trend in the mean as an option. We discard the trend in the mean as an option under both the LN2 and LP3 distributional assumptions. Next, let's look at quantile regression. This is, again, this is an empirical method that we're comparing to distribution-based fits, and therefore yields the exact same result in both the LN2 and LP3 graphs. So it's the exact same in both bar plots. However, it is substantially below the flood of record on both graphs. Now, while the flood of record in theory can have a recurrence interval above 100 years, there is another important issue with quantile regression. The largest flood took place earlier on in the urbanization process. So as a result, the quantile regression model estimates a decrease in the 100-year flood. For this reason, we eliminated quantile regression from further consideration. Next, I'm going to want your opinion on the remaining options, as the choice is not so clear-cut. Interestingly, the only estimate above the 100-year flood is the LN2 estimate with no trends. While this no trends model does not incorporate important changes in the watershed, one may argue that it nevertheless yields a pretty reasonable estimate of the 100-year flood and reflects a lack of change in extreme floods at the site. We also see that the model with trends in the mean and variance for the LN2 distribution produces an estimate well below the flood of record. One reason for this is that the change in variance is not symmetrical. As we can see in the graph of the floods, we see that the small peak flows rise a lot, while the large ones don't change much at all. One other thing I want to point out is a comparison of the LN2 and LP3 distribution. So comparing the top bar plot to the bottom bar plot, the LN2 distribution no trend model has a much higher estimate than its trend and mean and variance model. However, these two models yield about the same estimate for the LP3 distribution because the LP3 formulation allows for a change in skewness to compensate for the change in variance. So now I want to turn it over to all of you and ask you which one would you choose, given what I've shown so far and what you know about flood frequency in general. So choice A will be an LN2 distribution with no trends that's slightly above the flood of record. B will be an LN2 distribution with accounting for a trend in the mean and variance, which is substantially below the flood of record. C is an LP3 distribution with no trends. This is what you would use if you followed Bulletin 17C. And D, you would look using an LP3 distribution, but with a trend in the mean and variance. You can also select E if you think another choice would be better than any of these, or if you are completely lost, please be honest. I know this is a deep dive into stats, especially for the first presentation of the day. So we'd love to hear that so we can improve future presentations. And Victoria, could they look at this for about 20 seconds and then before you post the poll question?
Oh, I already put it up. I'm so sorry.
Oh, okay,
but
sorry.
About 42% of them have voted already, and I'll be honest with you, the E didn't fit. So I took it off, but I would imagine nobody would be lost. I mean, I'm sure you're all had lots of coffee this morning and you're on it. So, but if you do feel you're lost, just drop us a comment in the question box and we'll make sure to share that. Someone did state in the comment box that true, this is a deep dive, but it is well worth it. So Jory, just let me know when you're ready for me to pull the poll question down. We have over 60% who voted.
Let's wait about 20 more seconds.
Okay. Yeah, we're almost to 70%.
Great. And I'll tell you what I'm leaning towards at the end. If I didn't make it, if I didn't make it, give a hint while I presented the slide.
Close it down and I'm going to share the results. We have 30% who picked D, 24% who picked A, 18% picked B, 15% picked C, and 13% chose other.
Other or lost? You can be honest.
Well, lost wasn't an option. I didn't have room for it.
Oh,
Sorry. But there's a
It's
couple
okay.
comments that have come in the question box that we'll share with you. All
Okay,
right, I'm going
that would be
to
great.
hide the survey here, and it's back to your screen. Thanks.
Okay, great. Well, I only have a couple more slides, and then we can discuss this. So, okay. So now moving on, some of you might have been wondering if it's possible to apply the same method using climate covariates such as annual precipitation or seasonal temperatures instead of using urbanization indicators such as impervious cover. And the short answer is that yes, you can extend this approach to accommodate climatic variables, but you need to be very careful. First, you need to make a judgment as to whether the trajectory of change is going to continue, level off, or switch directions over the course of the design life of your infrastructure. This can get tricky with climatic data since apparent trends may be really short-term changes in longer-term cycles. It's best to use design floods updated for current conditions to design infrastructure for a lifetime over which subsequent changes are unlikely, or else you would have to make this even more complicated. Another reason you can't apply the method I just showed you so readily is that you can't compute the 100-year flood conditional upon the last year of a precipitation record in the same way that you can do it with urbanization, because if you have an anomalously wet year like this one here, you're going to get a distribution that's really high. It's gonna think that the mean flood is this really anomalously wet value, so it's going to give you an overestimate of your 100-year flood. So you need to be really careful. And we're working on a method for making these adjustments when you have fluctuating climate variables, and we're doing this with a case study at a station in Grand Forks, North Dakota, along the flood-prone Red River of the North. Unfortunately, we didn't have time to show this today, but in a nutshell, here are some key steps. First, one needs to adjust covariate peak flow relations for trends present in the covariates. Then you need to adjust the peak flow observations to reflect these covariate trends before computing the design flood from these trend-adjusted observations. So don't go home and try what I showed you with urbanization adjustments on climate adjustments just yet, but we will have a paper or report that will publish this work. So to sum things up, I'd just like to add a few concluding remarks. First, methods that account for changes are essential for design peak flows. Second, changes in peak flow variability can affect design flood substantially, especially in urbanizing basins. My prior dissertation research shows this effect in numerous other basins across the country. So if you're wondering whether the River Rouge case study is a special case, you're not going to see it everywhere, but there are quite a few other basins in which we see this effect. However, urban basins can also be quite idiosyncratic since there are so many other things going on in addition to impervious cover. And what I'd like to look at in future work is the effects that stormwater infrastructure construction may have on the reduction of peak flows. Third, it's also possible to make changes for climate adjustments, but these are more difficult and complicated. For instance, you need to consider whether apparent trends have sustained change signals, and if so, make adjustments for temporal trends in your climate covariates. And if I wasn't clear before, climate covariates are the independent variables that you use in the regression models to adjust design peak flows. And I'm happy to answer more questions about this or talk to anyone who's interested in the topic more offline. And finally, I'd just like to end by reiterating that non-stationary flood frequency research that accounts for environmental changes is still very active with many open questions. And one particular question that I'd like to focus on in the future is the evaluation of regional methods for predicting changes at ungauged sites, as the methods I've shown you today are intended for adjusting records at gauge sites. However, our immediate next step will take a bigger picture view of changes in changes in flooding and their impacts on infrastructure. As many of you indicated in the initial poll, you have a strong interest in there's a strong interest in bridge scour in the transportation community. And with that information, I'd like to tell you that, and make a shameless plug, and say that we'll be investigating additional streamflow metrics and hydrologic forcing factors to help the Federal Highways Administration understand channel change and bridge scour. And with that, I'd like to thank you for your time and bearing with the initial technical difficulties. So, and I'd really appreciate it if you could fill out our short handout. And I have this handout includes a few questions soliciting presentation feedback, and also a few questions about flood frequency training. And since I wasn't able to get a web form approved on time, I would really appreciate it if you could email it to me at jhecht@usgs.gov. And with that, I'd like to take questions if there's time.
Okay, there's a few questions.
Mm-hmm.
Is Atlas 14 mean precipitation available online?
I believe that it should be available somewhere. I'll have to check because we're actually not using it in our study. I just put it there as an example of a common practice. So I can get back to, if the person who asked this question could email me, I'm happy to look into this and get back to them.
Another question was, what about other variables? Disconnection of impervious cover, stormwater management in individual watersheds?
No, that's a great question, and we would like to include that in future work. The idea is what we're doing here is we're using impervious cover as an example of one covariate that has a relationship with peak flows. But as I suggested on the last concluding remarks slide, we'd like to also add other variables of representing impacts of urbanization, such as stormwater management, for example. And I'd also like to clarify that, while we illustrated this method with just one explanatory variable to keep it simpler, to make it simpler, we can definitely extend this work to include formulations that look at multiple covariates as explanatory variables.
Okay, there was just another question about, did any of the counties within the watershed in your first example require detention for developments?
Yeah, so I believe that some Michigan has implemented some stormwater regulations, since not for all of them in the beginning, but I would say that one thing to look for in future work would be as stormwater development, the stormwater requirements have increased over time. Does the same increase in impervious cover have the same effect now as it did, say, 50 years ago? So in addition to there being a faster growth rate in the 60s and 70s, 50s, 60s, and 70s, it'd be great to see not only whether it's just that there's more impervious cover being added each year then, but also to see whether or not the impervious cover that is added has a greater, say, per acre impact on peak flows because there are fewer detention requirements, or there were fewer detention requirements 30 or 40 years ago. So, great question.
There's a couple other questions, but we're run out of really time. So I think your questions will be provided to the presenters to be answered later.
Okay.
With that, we'll move on to the second presentation, which is site-specific hydrologic and hydraulic analysis for assessing transportation infrastructure vulnerability and resilient design for bridges in Pennsylvania by Donna Newell. Donna Newell is president and co-founder of NTM Engineering, Inc., a women-based business that specializes in water resources, structural engineering, and course development and instruction. Ms. Newell earned her BS in civil engineering and MS in environmental engineering from the Pennsylvania State University and holds a professional engineering license in Pennsylvania and is a certified floodplain manager. She has over 20 years experience performing hydrologic and hydraulic modeling, bridge scour analysis, water permitting, and floodplain studies. Okay, Donna.
Thank you. And I'm sure we have a few Penn Staters on the call, so I thought I'd do the conference in my conference room that has our Penn State Nittany Lion for any of you Penn Staters. So I decided with this title I would go for the longest title in the presentations over the next few days, so I won't repeat it again. Okay. So this pilot study is going to discuss the pilot study goals and briefly touch on the projected precipitation changes. I will spend the majority of the presentation focused on the hydrologic and hydraulic modeling results for the 3 specific sites that we modeled. And then we will talk about the applications to the PennDOT design process and some of the adaptation strategies that we're looking at related to PennDOT sites. This pilot study was funded by Federal Highway and PennDOT and supports PennDOT's continued effort to develop processes and procedures to assess potential flooding vulnerabilities and risks related to the transportation infrastructure. And really the primary goals of this study was to look at how do we address the climate change in the H&H studies. One of the things that were considered were using ratios or adjustment factors to increase existing precipitation. What range of ratios are reasonable? Do they vary in regions across our state? Pennsylvania has a lot of varying topography and climate across the state. And so that's why we looked at 3 particular different parts of the state for this study. And then would the higher precipitation events result in changes to the design? What adaptive design strategies might we want to consider to improve resiliency, and how much would they cost? Now in this presentation, given that it's 20 minutes, I'm not going to get into a lot on the cost considerations. We do have a pretty in-depth report that was developed for Federal Highway that does get into some of those details too. So looking at the sites that we've selected for this study, the 3 sites were selected representing Western Pennsylvania. So you can see the red star in Allegheny County. The site is very near Pittsburgh. And then additionally, we looked at one in South Central Pennsylvania in York County, which is close to the Maryland border. And then further south in Eastern Pennsylvania, very close to Delaware, or very close to Philadelphia in the Delaware County area. For the 3 sites that we looked at, we used modeling methods. We used the Watershed Modeling System, WMS, to develop the basin characteristics, and then the peak flows for the existing and future hydrologic conditions were developed using Hecht HMS. And we considered future land use in the watersheds where that was applicable or where there was anticipated future land use. I can hear a lot of background talking. Is that?
I can too, but it looks like it's coming from, is that not going on in your area?
No, there's nobody in my office but me physically.
Well, that's interesting. Well, hopefully it's going to calm down here. I'll keep checking the system to see if I can figure out where it's coming from.
Okay, I didn't know. I was like, no, I'm the only one here.
Yeah. I'm looking and I don't see anybody else who has their audio connected like that. Oh,
Okay.
wait a minute. I see it. It's Jory, I think. I just muted him.
Okay, thank you. I'm sorry.
Okay,
it was
we're
just
good.
a lot of
No
feedback
problem.
in my
find
headset
them.
too. Okay,
You're fine.
thanks.
Thanks.
And then we used HEC-RAS for the existing and future hydraulic modeling. For this particular scenario, given the budgets of the projects, part of the hydraulic modeling constraints we're looking at some sites that may have had some existing HEC-RAS models. So we did use one-dimensional HEC-RAS modeling. And again, more so to look at the overall trends in water surface increases and velocities than dealing with a lot of the details the 2D might have given us. So I'm going to talk a little bit about the climate models and the representative concentration pathway scenarios that were considered, but this was developed by Michael Baker on the project. Many of you may know Will Thomas was responsible for a lot of this work. And what was determined in this, we looked at various scenarios. Ratios were estimated for both year 2050 and 2100 using both the RCP 4.5 and RCP 8.5. And we also looked at 8 different climate models. There were a lot of scenarios considered, and early on we spent a lot of time doing some different hydrology methods for a lot of the different models. For the final pilot studies, so that we could provide results from existing to future, we did use the year 2100 with RCP 8.5 for annual exceedance probabilities ranging from 0.5 to 0.002. There were significant variations in the ratios across the 3 pilot studies across the state. The Baker Road site, which is the York County in the center of the state, had the highest ratios, and we'll talk about that a little bit more. And there was more variability in the ratios for the extreme events. For the 0.1 annual exceedance probability event and less, the global climate model ratios are greater than 1 for all of the GCMs that we looked at, which implied increased future precipitation for the more frequent events. As we looked at some of the higher, greater annual exceedance probability events, we did see some of the global climate models dip below 1, indicating decreases, which just showed some of the more issues with some of those larger inconsistencies in some of those larger events. So these 3 figures on this slide show the ratio of the future precipitation to historical precipitation developed for each of the 3 sites for the 8 different models using the 8.5 RCP for year 2100. Now, the thing that's important about this particular slide, and I have York counties as the larger slide on the left, all 3 of these have the same y-axis, which ranges from 0 to 5. And what you can clearly see just quickly looking at the graph is that York County for several of the models had very high, much larger predicted ratios for several of the models compared to Delaware County and Allegheny County, which had varying ratios calculated and some that for the higher annual exceedance probabilities went below 1, but much more consistent. For Delaware County, our range was 1 to 1.76. For Allegheny, our range was 1 to 1.51. For York County, our range was less than 1 to 4.5. So a lot of variability in that data, indicating some of the uncertainty in the global modeling process, and particularly the uncertainty as we look at those higher annual exceedance probabilities for those larger events. So based on that and some recommendations in the CHRP 1561 study, which recommends considering using the 0.1 AEP ratio for the more extreme events because of the current ability of the high resolution data sets to represent the precipitation extremes, we looked at and decided to use the 0.1 AEP for all 3 sites. And for simplicity of the modeling, we did apply it also the 0.1 AEP to the 0.5 and the 0.2 AEP events, just so that we were consistently using the same ratio for all of the events that we considered. And there was not a huge difference in those 2 lower events anyways. So what we ended up getting is for the Allegheny site, we have a ratio of a 1.24, which in essence is looking at a 24% increase for year 2100 100 with the RCP of 8.5. Delaware County was our lowest at 1.16, and York County with this 0.1 AEP was down to 1.25. If we would have used York County with some of the higher events, you can see in the bright yellow in this figure how much higher that ratio would have been for some of those other return periods, closer to 2 out there for the 0.002 AEP. So these are the values that we used for our precipitation ratios as we looked at our future conditions. So now I want to move into discussing initially the H&H results for the 3 pilot studies, what the study, some of the information about the studies, and then we'll get into the applications within PennDOT's design process and possible adaptation strategies later in the presentation. So our first site is SR 2046 along Streets Run in Allegheny County. This is the one in western Pennsylvania near Pittsburgh. The SR 2046 or Streets Run Road or Baldwin Road was selected because of the history of lateral flooding along SR 2046, as well as the landslide susceptibility within the watershed. The site is located in a FEMA Zone A study area, and the FEMA map shows the SR 2046 through the Streets Run floodplain. If you look at this figure on the left here with the FEMA map, the red dashed line moves through the floodplain and in and out of the floodplain, and this is SR 2046. The stream actually runs and meanders around through this development and curves back in and around, and this is all housing developed in this area. The 2 pictures on this page give you a little bit of representative of some of the frequent flooding that this housing area near SR 2046 received pretty frequently. And you can see if you look at the top picture and you look at the shrub, and then you look at the bottom picture, that same shrub that we have a circle around is showing how close the stream is to this backyard and the type of water they see flowing across their yards. This was just July 2019. This actually was probably about a week and a half prior to our site visit to this area, so we were able to get some pretty nice photos from locals. The design, if this road was designed today under PennDOT's current criteria, it would be designed as a minor arterial roadway with a 0.04 AEP design event. The Streets Run Watershed is an 8 square mile watershed, which is steep and heavily forested in sections. As you can see through part of this watershed on the left, you can see a lot of the heavy forested development. This is also a lot of the steep areas with the landslide susceptibility. And there's also highly developed with mixed commercial and residential development. The photos on the right show a few different views along Streets Run. The upper photo is showing us an area where we have some walls along Streets Run with the road right adjacent to the stream. The area on the bottom is another section of Streets Run adjacent to the road. And what we're seeing here is it's one of the areas where we have bends. You can see some of the embankment protection on the upper part of the photo. And then as it comes around the bend, the embankment protection is either gone or was not there ever. Just not a lot of stability in this stream section. As we talk about some of the results in the projected conditions that were calculated using that increased precipitation for future conditions, I want to talk about the figure on the right first to just orient you to what's in this table. The figure on the right is showing the flow as it moves from the bottom of the page downstream from cross-section 7430 as it moves downstream to cross-section 4160 and Ramp Street. Now, as Streets Run moves through this area, it crosses through numerous bridges, meanders back and forth, and SR 2046, which is again is this red dashed line through here, is meandering in and out of the floodplain of SR 2046. So For this particular study, what we are doing because of the lateral flow is showing cross sections along the 5,000 foot long reach and some of the results that we saw within that reach. So for instance, for the design event or the 0.04 AEP, if we were to design this road today, we were looking at water surface or flow increases of 1,400 CFS for the 0.04 AEP and over 2,500 CFS for the 0.01 AEP. So for a 24% increase in precipitation, we're showing approximately a 40% increase in flows for the 0.04 AEP and greater than 50% increase in flows for the 0.01 AEP. So the future condition water surface elevations are projected to increase, given that we have these significant increases in flows, up to 1.35 feet for the 0.04 AEP and up to 1.9 feet for the 0.01 AEP. And that varies along the reach. You can see in this table here that at some of the cross sections, we have lower increases in water surface elevation, and then some of the downstream cross sections have much higher increases in water surface elevation as the channel gets more constrained in that lower section. And although we have increased water surface elevations, we didn't have significant velocity increases, not drastically through the reach. There are some localized increases at Ramp Street Bridge and some of the other structures, but pretty much in existing conditions, some of these return events are already getting out of bank. And so the increases are really going to be looking at the increased frequency and how frequent these are going to be getting out of bank and over this road. This particular figure, and we're not going to spend too much time on this, but this is just showing a localized zoomed in. The blue line is representing the stream as it moves through here. SR 2046 meanders in the floodplain here. It's out of the floodplain here. This is actually a steep embankment that really is setting up that the flows won't encroach significantly over this embankment in this area. So the purple line is showing the existing 100-year or 0.01 AEP, and the green is showing the projected future condition. And although it doesn't look like extensive increased floodplain width in this particular area, what we are going to see is just more frequent, the lower event storms are going to be over, particularly in this section here where Streets Run is directly adjacent to SR 2046. We're going to see the flow overtopping the road much more frequently. As we move on to the next site, the Baker Road over Little Conewago Creek is in York County, and it was actually York County Bridge number 177. This site was selected because of the history of roadway overtopping at the site, and the site was currently under design for replacement. So if there were some resilient design strategies that might be beneficial to consider in some of the replacement, it was a good site from that standpoint. The watershed is a mixed use. In this particular watershed, we have agricultural, commercial, and residential development, industrial use. There are a couple quarries within the watershed. And additionally, there was carbonate area under this watershed, which made this site a little different, and we'll talk about that on the next slide. And then for future conditions, this particular watershed did have an area that was zoned for some potential future development. And so we did consider that also in the land changes for future development, in addition to the precipitation changes. The site is located in a detailed study area and is a rural collector roadway per PennDOT's classifications with a 0.1 AEP design event. And you can see in this photo on the top, this is a flooding event from 2013, which was a little less than 5 inches, and we had 25-year event. So what you can see here is that we actually get roadway overtopping at this site on the approach road well before the bridge is actually inundated and overtopped. And how is that going to be a consideration with future conditions? The two figures we're showing here, the one on the left shows the 20 square mile watershed And the one on the right is the one I want to focus a little bit on. The dark purple shading is representing the carbonate geology that underlays the site, and it actually accounts for about a little less than 24% of the watershed. So we did consider that in using some reduction factors to the flows used in the HMS modeling with the modeling to consider that carbonate as we looked at this site. And again, the table on this slide is showing the bridge conditions more so because this is more of a bridge than a lateral road flooding. This table is showing the upstream water surface elevations immediately upstream of the bridge and velocities for the 0.1 AEP event and also the 0.01 AEP event. For this particular site, and again, this was York County, before we adjusted and used the lower ratios, this would have potentially, for some of these higher events, had much higher ratios if we wouldn't have averaged down to the 0.1 AEP for consideration. So we had 1,650 CFS, or a 58% increase for the 0.1 AEP, and a 2,700 CFS increase, or 41% for the 0.01 AEP. So pretty significant flow increases, and the flows in the water surfaces are increasing significantly. The water surface increased by 1.68 feet for the 0.1 AEP and 1.84 feet for the 0.01 AEP. The increases in velocities were relatively minimal due to how wide the floodplain is, and I'll show you that on the next slide. Because the flow is really moving out and over the floodplain for those larger events, we didn't see significant increases in the velocity. You know, a little bit of localized, but not drastic increases. Due to more frequent inundation of the bridge and the bridge deck with future flows, there are going to need to be additional considerations for uplift and overturning, which is something as a hydraulic engineer I don't typically think about, but working with our structural engineers and talking to them about some of the conditions with how much more frequently this bridge could be inundated and potentially overtopped, that was something that we will look into in the strategies that we look at later. This is showing the Baker Road projected floodplain. The existing floodplain is shown, 100-year or 0.01 floodplain is shown in yellow. And in green, we can see the proposed or future potential floodplain. And what is interesting here, as we looked at various ratios, this floodplain in the green lines here along the left north side of the picture really show that future conditions could show increased impacts to this housing development immediately local to the bridge without any changes to the actual bridge, just from future predicted flows. We also, and I didn't get into showing this in these slides just from the period of time, but we also looked at velocity distributions for the flow. A lot of the flow occurs in this left overbank. Flow is moving from the bottom of the picture to the top of the picture, so this left overbank. And we looked at would increased velocity distributions across there make that embankment, and more frequent overtopping, make that embankment more susceptible to erosion, and could there be some things there to consider? So those are some things that would be looked at in resilient or adaptive strategies. As we move to the last site, the study is Delaware County Bridge along T314, or locally known as Station Road, and it's over East Branch Chester Creek. This site was selected also because of a history of overtopping and a potential future replacement. You can see the current existing bridge in the picture on the top of the screen, and then the floodplain is presented in the bottom of the screen. The watershed is a mixed land use watershed with agricultural, commercial, and residential. A large portion of the Brandywine Airport is in the watershed, so that's an urbanized section. There were no anticipated large land use changes anticipated. The watershed is fairly developed. in a good part of it, and where it is agricultural in some of the undeveloped areas, some of those have requirements to stay in those zones. So it was also a FEMA detailed study area, and per PennDOT's current classifications would be a rural collector roadway with a 0.1 AP design event. Again, the flows that we're seeing increasing here show a 2,200 CFS increase for the 0.1 AP, which is a 56% increase over existing, and a 4,400 CFS increase, or a 45% increase for the 0.01 AP. And the flows in the water surfaces were increasing significantly by about 1 foot for both the 0.1 and the 0.01 AP. The increases in velocity, again, are not drastically increasing, again, due to this wide floodplain and roadway overtopping. And again, this one would be another one where, considering some of the additional bridge consideration design criteria for overturning, uplift, that might need to be considered. The thing that was interesting about this site is really the watershed. So the flow for this site is moving from the left side of the screen and meandering through this floodplain to the right. Our bridge is in this area. And the existing condition is this light blue shaded area, which did not overtop the roadway through here in the existing for the 100-year floodplain. As we look at, and I'm going to zoom in here, as we look at this area for the future predicted flows, now this section of the roadway in this area right here is showing that it's going to be inundated and really restrict the traffic that can move through this area that would have previously been able to move through this area. So that's something that would have to be looked at in the sensitivity to, is there benefit in possibly raising this side road? Our study road is actually over here. So this is an adjacent roadway that may need to be looked at as future flows from the overall stream or flooding out to that area. So that's a summary of the various 3 sites that we looked at, and sort of just the general hydrology and hydraulic results for those future conditions. Now we want to look a little bit on how we evaluated the 3 study sites for PennDOT design processes, and also some of the adaptation strategies that we were considering. In specific, the current research has aimed to address some of these questions. How should those precipitation ratios be applied within the H&H process? What future precipitation ratios are appropriate for application? We looked at 3 different sites across the state. We may need to look at more. We have some regional variance within that. What hydraulic parameters should be evaluated under existing and future precipitation scenarios to look at or identify resilient design options? And what resilient design options should be considered? Although we need more research and evaluation is needed before we can look at finalizing some of these climate prediction methods or formally integrating them into design manuals and processes, we did develop several checklists and resiliency considerations that we will discuss on the next few slides that may be closer to implementation in the PennDOT process. In particular, we developed 2 resilient design checklists to assist in the evaluation of the need for various resilient design options, a bridge project checklist, and also a roadway parallel to streams checklist. These checklists were developed considering interdisciplinary concerns more so than just the hydraulics, and we will show you some of the different things that were looked at. Because every site is different, establishing ranges or thresholds for checklist parameters is not practical. When determining the level of potential for resilient design, engineering judgment, the interdisciplinary coordination, and knowledge of the existing conditions at the site are really important to evaluate, related to risk posed to the physical infrastructure and the traveling public, a comparison of the existing and future parameters, and even magnitudes of those future parameters and their effect on the performance. As we looked at these checklists, and we're going to show you one on the next slide, we struggled with picking those specific ranges. So instead, we looked at this low, medium, and high to sort of try and envelope things that as we looked at the results, things that we thought were minor or maybe not necessarily worth special designs for resiliency, we classified as low. Things that may be more sensitive to resiliency designs and may be worth looking into in more detail, we classified as medium. And things that we thought resiliency design modifications would be highly recommended, we classified as high. These are not, this is our attempt to sort of look at this. We had coordinated with PennDOT on reviewing our draft checklists, and they had suggested some updates, and we had also coordinated with Federal Highways. Eric Brown had looked at them and several others and made some suggestions too. So this first bridge checklist is the bridge checklist, looking for, it consists of interdisciplinary parameters, including hydraulics, safety, that are compared between existing conditions and future conditions. For instance, we have site data in the top of the checklist where you can see we're talking about, and just summarizing some things too, what methods were used, if there's embankment instability or overtopping frequency. And then one of the things that becomes important as we think about risk is this provide access to critical services. Are there detours available? Is this, what's going on at this site? Because that might make other things more important for a particular site compared to if there are a lot of availability and this isn't a high parameter. And then we get into, and this particular site we're looking at is the one for the York County site. And if we look at these red boxes that are highlighted here, we have parameters for the design event and then also parameters for the 0.01 AEP event. And you can see in the highlighted boxes, the more concerning items for this site are related to the overtopping velocities and depths. And one of the structural concerns with this is considering that uplift and overturning that might be considered as we look at having more depth over the roadway and actually over the bridge deck. A lot of times in Pennsylvania, we have a lot of road or flooding over our approach roads, but our bridge decks are not fully inundated. But in this particular situation, we're actually looking at, in this bottom red box, the fact that in the existing condition, we have less than 0.2 feet showing over the structure, whereas in the future condition, we could have up to 2 feet over the bridge barrier. And that will significantly impact what could be happening in some of those other forces with the bridge. Oh, sorry. I went too fast. The next checklist we looked at was the roadway checklist. And this was developed, and the one you're looking at is for the Allegheny County site. As we were developing the Allegheny County site, although there are bridges in that reach, what we were really looking at in that site were some of the embankment concerns as the stream was parallel to the roadway. So we actually looked at a couple different things for this site, and this checklist looks a little different in that we're considering scour and stability for roadways. And as we look at that scour and stability with lateral flow, as we consider lateral scour, bank full flow becomes a more important factor in lateral scour. So you can see that this checklist shows not only bank full flow, but the design event and also the 0.01 AEP event. So as we move on, we'll look at some design events or design strategies, and I know we're getting low on time. We looked at evaluating some risk-based approaches for considering strategies for these pilot sites with risk factors which could include potential loss of life, length of the detour if the road is closed, average daily traffic, emergency services, significant erosion if we have more frequent overtopping, and what types of strategies are we going to need to consider. Larger hydraulic openings, bridge design changes, pavement materials, scour prevention strategies, inspection maintenance procedures. These are all things that were considered. Some of the adaptation considerations for the pilot study sites, for sites with more frequent inundation, of the bridge deck. One of the things that came out of this that I honestly, as a hydraulic engineer, wasn't thinking about initially was related to some of the resilient design of the bridge to address uplift and overturning, including mechanically restraining the bearings, adjustments to dowel bar designs, whether they be longer bars or deformed bars, to help deal with some of those things. We got our structural engineer involved in doing some test cases and some cost benefits that we presented in the actual report. We looked at increases in the hydraulic opening of the bridge, and in some instances that may be beneficial, but in both of these studies that we had significant roadway overtopping in, there's a very sensitive issue, because as you increase the roadway profile, or as you increase the bridge opening, the roadway profiles go up, and it sort of was a negative benefit as it caused increases in water surface elevation, and it was not as much beneficial. So in some instances, increased hydraulic opening may be very beneficial, but in our particular, two of our particular sites, it was not.
Well, it looks like Donna's having a technical issue there. So hopefully we'll have her reconnected here in just a second. In the meantime, I do want to mention that we've requested the handout from Donna, and that it'll be added to the webpage of handouts for the conference. I'll be emailing out a link to that to everyone after the session concludes this morning. And the handouts for this afternoon's sessions have already been loaded to that webpage as well. So hopefully we've got her reconnected. Hi, Donna, are you back with us? Looks like she's logging in here. There we go. We can see your PowerPoint again. Not hearing your audio though. Can you go ahead and go to the audio box and do that toggle between the phone call option and the computer audio, and hopefully it'll reset your audio connection. It does look like we're going to run over a little bit on time today. Are you there, Donna? I'm still not hearing you. Did you open the audio panel and just select the phone call option button? Talk again, Donna. And then toggle back to computer audio.
We are trying.
We hear you now. Okay,
Okay,
keep going.
thank you.
Thanks.
Sorry, I had my power plugged in, but it was not working, so I had a backup in here. Okay, are we still seeing my screen?
We're seeing the PowerPoint, but it's not in the full slide view. I think if you just put it back in the, well, there we go. We see the thank you slide. Go back a couple.
We were almost done. Okay. So we were on this slide. So just a few
box. There we go. Okay, I see it now. Thanks.
Okay. I'm sorry. I had my power plugged in, but I had to switch to a different cord. So a couple of the other things that we came up with adaptation considerations were embankment protection, where the frequency of overtopping is high. Looking at velocity distributions along the embankment may be relevant as we look at areas closer to the bridge. May we need to extend that embankment protection a little further if those areas are going to see higher velocities. And then evaluating changes to scour protection options where velocities are increased, or in situations where we may see pressure flow occurring for future conditions that we didn't see in the existing conditions. And that may change some of our scour design. For sites with lateral flooding along the roadway for existing walls, we may, for sites that have existing walls, we might need to look at evaluating the level of protection needed at the toe of those existing walls. We may need to consider underpinning the wall with micropiles or replacing scour-prone soil. An alternate to underpinning would be looking at channel lining. That becomes a sensitive area in some environmental areas. Our Allegheny County area is not particularly a high quality stream, so it wouldn't be as particularly sensitive there as it may be in some other areas with more pristine environmental conditions. And then replacing the existing guide rail and pavement at the edge of the road with a reinforced concrete moment slab and single face concrete barrier, not to provide necessarily a flood levee protection type of thing, but more so to help prevent the frequent overtopping from damaging the roadway, just keeping it on the stream side. So those are some things that we considered when we had existing walls. For areas that didn't have existing walls, but we may see a lot more frequent erosive potential, looking at new walls might be something that would need to be considered. Previous. So those were some of the various different considerations that we looked at and are documented in the detailed study that we developed for Federal Highway. And in the order of completing the presentation, just wanted to thank everybody for listening to our presentation. Sorry for the brief technical difficulty. And if there is a second or two, we can take some questions, or
Donna,
if we're running over.
Yeah, we're running over. We'll take
That's fine.
them at a later time and move to the third presentation. Thank you, Donna.
Thanks.
Michael, can you hear me okay?
Yes.
Okay.
Okay, our third presentation is Arizona DOT USGS Partnership Advanced Water Data Collection and Modeling for Design Engineering, Flood Forecasting, and Resilience Building by Steve Olmsted. Stephen Olmsted is a program manager for Arizona DOT Environmental Planning Innovative Programs Major Studies. Mr. Olmsted assists with delivering ADOT's $1 billion annual construction program. He currently oversees programs for sustainable transportation resilience, 2D, 3D, LiDAR design, engineering integration, a USGS water modeling partnership, and assists FHWA with national state DOT innovation adoption. All yours, Steve.
Thank you, Michael. I appreciate it. Good morning, everyone, and good afternoon for those of you that are a little further into the day. So I know we ran a little bit over on time, so I'll be somewhat efficient. The way I did the presentation was to give a little bit more of a resource opportunity. So it was not intended to present every detail on every page. I wanted people to be able to go to the PowerPoint and then look through it and go from there. So I'll balance the overage and move through things quickly but fairly. So again, this is a little bit more of a programmatic discussion. We looked at two different presentations from Jory and Donna. This one's a little bit more of a program effort. The two things I really would like everyone to kind of take away is how the partnership has changed the way we account, monitor, and model water, and how this approach has dramatically changed the inputs to hydraulic engineering and overall project development at water crossings, especially for projects between 5 million and 100 million for ADOT. The second takeaway is the process ADOT has developed to enhance how H&H has been incorporated into design engineering and extending that into lifecycle planning, asset management, operations, and resilience. I don't want to spend too much time on flood forecasting. I did want to mention it because I wanted to recognize that from the standpoint of operations and also hydraulic engineering, there's some consistency and there's some outputs there that are really beneficial. What you're looking at is a GIS dashboard. It was a July 2020 wildfire for us. It burned almost 200,000 acres. I can certainly be compassionate for everything that everybody's experiencing in California, Washington, and Oregon. that are millions of acres. 200,000 for us is a pretty staggering amount. It's the 5th largest wildfire we've experienced in the history of Arizona. What you're looking at is kind of a one-stop shopping GIS dashboard that we built, that USGS built, helped with us, and then one of our GIS experts who gets all the credit put this together. The takeaway here really is it's a single point of interaction for Forest Service, USGS, National Weather Service, ADOT operations, ADOT districts, the Resilience program, the Road Weather program, and the such. And the biggest benefit is the live feed. You'll see it down there in the lower right. And so the districts can look at where a weather cell is happening and see how it's migrating at, near, or over the burn area. The complementary product that was put out, and this is a little bit more where I'll mention the operations and the hydraulics piece, is USGS delineated 26 watersheds in the 200,000 acres and tied those to the ADOT drainage assets from there. So what we ended up with was the development of a pretty comprehensive debris flow risk matrix to help with decision making, prioritization, and our Federal Highways ER application. So let me turn to the partnership now specifically. You know, over the last 6 years, we set about advancing evidence-driven decision-making, contribute to further blending risk science, technology, and engineering to improve the understanding of water-related data collection and modeling, especially as it relates to H&H. The second part of that you can see at the bottom is the nice tie into our ADOT Resilience program. And as is common sense, 2 of the multiple aspects we look at in the Resilience program: intense precipitation and system flooding. There is a link to the, excuse me, the website at the bottom there. So what really changed? We experimented with a lot of different things that I'll talk about for several years, going on 6 years now, and that's fine. Very hard, as Donna pointed out, to get things actually implemented into guidance. So in order for us to really move to a level where the tools that I'll discuss were implementable, adoptable, and also appropriate to consider in H&H and then subsequent overall design, engineering, and project development, we spent a lot of years, all credit goes to USGS, to actually develop a publication. You see it there. It is a download in the attachments area, and it's fact sheet 2019-3073. I won't belabor it. You can download it and read it to your heart's content. But the gist of what we wanted to do was really improve the way traditional stream gauging worked or informed our structures. There's certainly a treasure trove of information from historic gauging around the state of Arizona. And that in combination with the StreamStats tool, it has been instrumental in helping the H&H community, both the internal ADOT and external consulting engineering environment, address what we needed to do. But the bottom line that we wanted to improve is that we just felt the traditional stream gauging just was not reflecting the topography and the clear geometry, the complex geometry that we really find in the Southwest. So again, without going into too much detail, again, you can read everything in the handout. You'll see the suite of tools. This isn't an all-encompassing list, but it's a large list. And as you can imagine, it was just improving how topography is captured, how vegetation conditions are captured, how the runoff is captured, and the such. The biggest change for us in what we've now moved to in reach scale monitoring is the addition of an array of sensors that are deployed throughout the river reach to remotely and continuously measure river stage and velocity. And this is especially beneficial in our remote areas where there may not be a traditional gauge available, or we want multiple years of information going into a design and then subsequent construction phase. You'll see here just some of the dynamic improvements in the topics and the type of information we're able to gather, and both or all these are contributory to H&H. Okay, I'll run through a pilot example now. So this is in the far northwest corner in Navajo country in Arizona. It's State Route 160, and you can see the severe wash meander. We have something out here. It's fairly unique to some of the Southwest states. It repeats itself pretty regularly here in Arizona. For those of you that have never heard the term oxbow, those are those wash meander activities to your lower left. But you can see at the south end of the bridge, the severe scour and erosion that was really pounding into that abutment, and the problems we were really having there. The ultimate decision was to go about, we spent about $1.1 million installing gabion baskets to both sides. They're pretty comprehensive. They curl out on both the north and south end of the bridge and both the upstream and downstream side. And so just to talk a little bit about what USGS provided, here's an output of the traditional stream gauging that's available upstream. What you're looking at is about a dozen low flow 1 to 2 year events. The 2 year, I believe, at this location was about 1,400 CFS. And the real benefit here was taking that traditional stream gauging information that was available from those 12 events and really combining them with this innovative suite of tools at the actual structure, and really learning what the outputs were, where there was benefit in better understanding the hydrology, where there were benefits to incorporating inputs into hydraulic design. And this is a location that we've been kind of monitoring for quite a few years. So what you're looking at here is 3 of those 12 events that I mentioned were overlaid into the point cloud data set to create some erosional change mapping detection, which the design engineering firm used to really validate and have that specific conversation about the exact length and locating of the gabion basket. So again, it was in its pilot phase. It wasn't a design engineering criteria requirement, but we were able to pilot the experiment. If you want to read a little bit further on it, you can see it here. It was in a TRC in November of 2017. So we don't really stop there. What you're looking at here is the animation side of the benefits of all the inputs we were able to gather. You're looking at a screenshot of a proposed 50-year event. Through the pre-construction, what we were able to do, even going into mid-design, was to look at the current conditions. And again, it's just the proposed storm event. We looked at the 50-year, the 100-year, and the 500-year. The benefits of innovation and technology, here you're looking at the same thing. This is a screenshot of the animation for the post-construction. And again, we were able to look at the same thing. We were able to see. Now you have to remember, we had the benefit of not really any extreme flows or high flows, but we did benefit by the dozen or more flows we did have. So I can't say we moved all the way to a calibrated runoff state, but certainly from a theoretical standpoint, we could tighten up what the 50, the 100, and the 500 year look like. And here you see final grading and seeding. So we don't stop there. Okay, that activity and construction completed in November of 2017. So for the last 3 years, we've continued to monitor how the structure itself is doing. What are the hydraulics? What's going on with that oxbow? You can see as it progresses toward the roadway. We've continued to advance erosional change mapping. You can see the benefits of technology and having continued runoff information. We can really take a look at how the hydraulics and the overall design engineering is holding up, because you can isolate into a specific area. Okay, so bottom line, fairly common sense. We increase accuracy. I mentioned all the suite of tools and some of the things we're experimenting with. We were able to validate them and get them adopted into ADOT design engineering. My biggest interest, you can see there in red, is to just, even though we're experimenting, we're constantly improving, we're doing proof of concept ideas all the time. It's really just to improve the modeling dynamics and really better understand the conditions before, during, and after, okay? And that after there, you start to see the tie into life cycle planning and asset management. This would be very difficult. The first 4 or 5 years we did this, I had stacks of external hard drives on my desk. You can imagine the size of these data sets, no matter what we're capturing. USGS built specifically for us a location in their USGS science base for all this information on every project we do. And the same goes, they built a dedicated Earth Resource and Aeros location that houses the air flight LiDAR, photogrammetric drone, or terrestrial LiDAR data sets as well. So I'll finish up a little bit more on the linkages. I just really wanted to show how USGS moves from kind of watershed to the enhanced reach modeling, clarifying the vegetative condition, further maybe improving N values, and just that combined with the current topography really created just a great suite of inputs to import right into the hydraulic engineering environment. And in this case, we're talking a little bit more about 2D hydraulic engineering, in particular SRH 2D, which Federal Highways is promoting. And for the last 3 years, Arizona has been a big proponent in attempting to adopt that. Concurrently with the USGS fact sheet from 2019, that same month that came out, all credit goes to Federal Highways Hydraulics, Scott Hogan and his group in providing a peer exchange for the Southwest states. That really further introduced how we've developed these suite of tools with USGS, how they do. Now, everybody is geographically specific to the different types of tools and data sets that they need available. Again, these were developed to be much more Southwest, dry, flashy wash environment realities. So we really were appreciative of being able to introduce these things and see how they really start to integrate into the full hydraulics environment. I just wanted to mention one of our main pilot locations was State Route 93. It was about a 7-acre area super box that addressed Gunsight Canyon. You can see that location to the bottom middle. And it's really one of the major pilots we undertook to look, as you can see in the title, HECRAS 1D, 2D, SRH 2D, and Flow 2D. And then just the last couple of slides, I just wanted to give everybody a kind of a look at where we're at right now. All these tools continue to progress. And I just thought I would just very basically bullet the sequencing that we've gone through of one of our current projects. Now, watershed and reach modeling through a rapid deployment gauge and the continuous slope area process is integrated. Those multiple sensors that I mentioned are at this location that you can see in the upper right. You can see the San Pedro River is one of the major waterways in Arizona. It also has to the middle right, that bump out area is Dragoon Wash. And so that's all to the downstream side of the bridge, okay? So the sequencing is pretty straightforward. USGS does their hydrology analysis. Where we feel it's appropriate, we mobilize the sensors and the rapid deployment gauge is bolted onto the bridge, hopefully 2 years in advance. So we start to gather. Remember, it doesn't rain a lot in Arizona. So we're always hoping respectfully, without anybody endangering themselves, that we get some runoff. That allows us to process 2 years of true data. And it really allows us to kind of move from that very appropriate FEMA stream stats data environment. If we get some runoff, we can move to a little bit more of a theoretical rating curve environment. And then if we get, which we have here, we've had a couple of nice 11-foot peak flows out here, gets us heading toward a much more fully calibrated reach rating curve. We had to use high res airplane LiDAR flight here to get through the thick vegetation, which you can see that cross section there in the middle in blue. All right, it was very successful getting to the ground, which we were struggling with on the overbanks. They're out here conducting the very traditionally the traditional 1D Hecht RAS, and we're doing SRH 2D here to model the complex geometry, and in particular the overbank vegetation realities, and that we really know, even though it's a very, very incised river, the 50-year event will overtop the embankments. And then the outputs, as we just get better and better at this, is kind of right-sizing hydraulics, and I don't want to lessen the importance of the scour. It's like the holy grail is better understanding scour, especially out here in the Southwest. The SRH 2D tool, among other avenues, has really improved the way scour can be looked at, and that's a big push to advance the scour tools for us at ADAP, in particular on this project. And then just the common sense output, measurably improved flow dynamics through this 3-span proposed design that you see at the bottom. Okay, last slide. We don't really stop there. I always like to just share one extra slide of what we're doing. Because we're 6 years into a lot of these data collection efforts, validating and doing the proof of concept for the different tools and seeing what the outputs are, getting the input from the internal ADOT folks, the decision makers, and also our external design engineering firms. We've gone a little bit further now, and we're looking at continuing on a pilot at this State Route 80 location of taking all the suite of information that we've gathered and start to move to a probabilistic risk decision-making process for our bridge asset class. So it is a pilot for us, and it has specifically an effort to look at live loading, extreme weather loading, climate-induced loading, and then obviously mentioning the data sets that we've been able to gather. And we really want to just develop a baseline methodology. Remember, it's exploratory, a baseline understanding of how we might compute the probability of failure given those different life cycle realities. And again, the reason is we just continue to want to move to a risk-based life cycle asset management effort. And so in closing, you know, really the hydrology has been measurably upgraded by USGS. And then we're very fortunate in the community. I think all of us, as the 2D environment continue to increase, and then the advent of just improved design engineering tools has really made it great for all these things to come together. Thank you.
Thanks, Steve. Thanks everyone for attending. That's the end of this session. Just a reminder that the virtual tour of the hydraulic lab has been postponed, and we hope to see you at the 2 o'clock session. Thanks.
Thank you, everyone. I'm going to end this session now, and you'll just need to use the same link to reconnect shortly before 2 o'clock. We'll see you then.